Hello, this is Team Supfina Machine, and our project is data collection using IIoT. We want to thank our technical directors, Mason Dumaine, James Los and David Dionyzopoulos, who are all URI graduates. Introducing our team, we have Natalie Cruz, who is electrical engineer, myself, Aaron Linares, electrical engineer, Jason Yang, computer engineer, and Hangsun Tran, computer engineer. Company overview. Supfina Machine is a company, one of the largest suppliers of abrasive finishing. They are located in North Kingstown, Rhode Island. The sister company is Supfina Grieshabe. Supfina Machine in the US is responsible to providing maintenance and building machines in North America, which include Canada, US, and Mexico. They specialize in finishing, super finishing, and abrasive finishing in the automotive parts industry, bearings, and flat surfaces. Our project motivation is to integrate a IoT system into these machines so that they are linked together, be able to track information that is needed to keep these machines running more efficiently and maintaining quality. So this helps with the customer demand, which is less downtime, faster, smarter machines, and the reduction of human labor. Also, see if these machines need maintenance if something isn't running correctly or the way it's supposed to. Now passing it on to Natalie Cruz.
Industrial Internet of Things is a digital network of industrial devices such as sensors, equipment, and machines that communicate with each other. This creates a system that can collect, monitor, analyze, and deliver new insightful data. IIoT is a stepping stone for industrial companies such as Supfina to grow, transform, and further advance their technologies. Clear benefits of an IIoT system are comprehensive monitoring, lower costs, and increased productivity. Comprehensive monitoring allows for predictive and remote maintenance. Being able to predict when a certain part will need to be replaced or being able to remotely diagnose a machine reduces costs from downtime and travel expenses. Process data helps better understand how clients are using the machines, which would allow Supfina to make informed decisions, tailor services, and develop machinery based on customer needs and usage. An increase in productivity is also possible due to errors being prevented, allowing for the identification and correction of inefficiencies such as energy or material waste. Final benefits include enhanced safety, where faulty parts may be proactively identified, decreasing the likelihood of injuries to operators and technicians. For this IIoT system, IO-Link is one of the preferred protocols of communication, as it is a point-to-point communication, meaning communication can occur between two separate endpoints. It is also bidirectional, which means data can be transmitted and received. Sensors and actuators are connected to an IO-Link master, which is the device that is connected to the Programmable Logic Controller, or PLC for short. An IO-Link master communicates to the field devices using IO-Link communication, but can connect to the PLC via different communication protocols such as Profinet, Profibus, or Ethernet IP, making it versatile and easy to integrate into existing systems. The project's anticipated best outcome will be the implementation of a modular, hardware and software-based IoT data collection system on existing Supfina machines, along with a web-based system to display, organize, and analyze the data. Team key technical accomplishments include IoT system analysis and communication protocols, the research and selection of industrial automation sensors, the consultation with outside company sales representatives, the preliminary hardware design, the learning of fundamentals of software tools and web development, as well as the finalized wireframe for the website. The economic impact for the company will be an increase in profit due to minimized downtime, thousands of dollars saved from travel expenses. The development of IIoT system would allow Supfina to showcase their features, offer packages to new and existing customers for their manufacturing processes. The savings would transform into additional revenue and allow the company to focus on expanding into other technologies. My technical accomplishments include the research for automation sensors capable of collecting data for airflow and consumption, temperature and humidity, and vibration, as well as the beginning stages of updating the schematics on the schematic software ePlan. The chosen sensor for airflow is capable of measuring not only flow rate, but also pressure, temperature, and consumption of air, which is beneficial in identifying if the air pump on the machine is properly functioned, as well if there is any loss, which would be considered an inefficiency. The sensor for vibration is the one on the left, which is called BALF BCM001, which conveniently can also measure temperature in addition to measuring the vibration velocity and acceleration, as well as the severity zone. The sensor on the right is BALF BCM002, which is similar to BCM001 but has additional features such as relative humidity and ambient pressure. These sensors are important in collecting process data as it helps better understand the details of the machine's performance and helps identify any errors that could negatively impact the product's superfinish. Future technical contributions include continuing to update the schematics, integrating the sensors on the machine, programming the PLC for data retrieval, as well as debugging the hardware. Aaron will now discuss the other set of sensors that were researched.
Individual technical contributions. We worked on the sensor list together and came up with the final parts list that we have. We worked on that individually and were in communication to see what the best options were and what worked and what didn't work, as well as working on the hardware design and what we think would be ideal for these machines. I will be covering the power meter sensor and the coolant flow rate and temperature sensor. Our power meter sensor is a AccuEnergy AccuVim2, which was recommended to us by the company. Ideally, we were looking for a power meter that could use either Ethernet or IO-Link, but we decided to go with an analog reading. So they recommended the AccuVim2 and the analog option extender. The sensor is intended to measure the machine's power and efficiency, to measure the consumption of the power. The machines are 480 volt industrial machines. They are 3 phases and they are 60 hertz. From the power meter, the analog signal is then connected into the PLC, which then communicates with the E1 Flexi, sending that to the cloud. We were looking at Schneider's power meters, but they were a lot more expensive and did things that we really didn't need them to do. So we went with AccuEnergy, which fit in our budget better and did what we needed to do. For the second sensor, we needed to also measure the flow rate and temperature of the coolant going in to the machine, depending on the environment of the machine and where it was. So we went with the IFM SA6010 sensor, which is rated for various liquids and air. This would be connected to the tubes where the coolant comes into the machine, and this is a IO-Link sensor, which is then connected into the IO-Link master switch, and from there into the PLC, which would be easier to communicate with the sensor and collect the data that we need. Next, I'll be talking about the industrial automation protocols. So the 3 main ones we were looking at were Ethernet, which is through a Ethernet, IO-Link, which is a M12 cable, and analog, which connects directly into the PLC's card. Analog is an option, but it's very limited to what we can do with the data we collect. So for the other sensors that we found, IO-Link sensors, the M12 is able to be connected into harsher environments, collect different types of data, and manipulate that way and send that to the PLC, which then can manipulate it in different ways and communicate with the sensor. And Ethernet also is an option, but that would be preferred to use in the electrical cabinet and is sensitive to the different environments where the machines are kept, depending on the facilities. So both Ethernet and analog are best kept in the electrical cabinet, and the M12 is able to be put inside the cases where the machines provide these finishes and can handle the high temperature, humidity, or coolant that is being sprayed in. The IO-Link also provides point-to-point wiring. The IO-Link master also records the configurations of the devices and automatically configures the new device to the way the old one was placed. And finally, my individual future technical contributions include hardware integration, PLC programming, schematic update, adding the new sensors into the original layout. And finally, when we implement the hardware into these machines, debug the programming as well as make sure the placement of the sensors are ideal. And now passing it on to Hung Sen Tran.
Hello, my name is Hung Sen Tran. I am one of the computer engineers on the team. A part of my team contribution was working on the web server. Before I begin, I wanted to take some time to explain how web development works. Web development is what makes the magic work behind the scenes. It can vary from a simple web page of text to a complex base internet application such as social media and online businesses. Everyone in today's age uses some form of web application on their mobile devices or computers. In order for me to work on the web server, I had to learn everything I needed to know about web development. One of the fundamentals of web development is its languages it utilizes. It varies a lot depending on what kind of application you are making. For that, I needed to learn JavaScript and HTML. JavaScript is a text-based programming language that allows the websites to be interactive. It provides elements that engage our users to the website. HTML is used to structure the web page and its content inside. On the bottom left corner, the team collaborated together and designed a wireframe for the web server. We plan on having the data shown in many different ways, such as data tables to line graphs. Not to mention, the web server will be withholding old data to be compared to the live data being collected. With the help provided from Amazon Web Services, we can store large amounts of data so that it will be utilized to view any discrepancies of the super finishing machines. For next semester, we plan on developing the framework of the web server. With our current pacing, I believe we can establish the basic functionality within the first couple of weeks. Not only we will be debugging the website, we will be assessing E1 Flexi connection to the demands of the server. E1 Flexi is an industrial modular gateway that provides universal connection. It also can send data to both local and cloud storages. E1 Flexi can support MQTT, which is a lightweight network protocol. It is used to transport messages between all kinds of devices. Aside from setting up the connection for the E1 Flexi, there will be long sessions of debugging afterwards. Now here will be our second computer engineer, Jason Yang. He'll be discussing how the hardware side of the project ties together with the software.
Thank you, Hung Sen. The portion of the project that I'll be discussing today is the connection between hardware and software within the IIoT system. The thread that connects them all is the Amazon Web Services platform. For this project, I researched this platform along with the DynamoDB service, which included a test program owned by Supfina. I also worked on the early stages of the web service implementation, namely the HTML code that displays the front end of a page. In addition, I selected the data plan to use for our database, which turned out to be the free version of Amazon Web Services, since any data cost beyond that would be inefficient. In addition to discussing these topics, I will also discuss what our computer engineering team will work on in the second half of the project. Next slide, please. DynamoDB is one of AWS's exceptionally powerful databases, capable of handling millions of simultaneous requests per second. It is our system's link between what our sensors read on the machine and the displayed data on the web page. Supfina has a test program for DynamoDB that we have been experimenting with, which takes sensor data from a Raspberry Pi and sends it remotely to our device, displaying data in our Eclipse IDE's console window. The eventual goal for our computer engineering team is to build upon this program so that our system's data collected and transmitted from the E1 Flexi can be accurately displayed on our web server. Next slide, please. This semester, our computer engineers have learned enough about web development to get started on the early stages of the web page. We have already integrated certain elements of the site in HTML using the Bootstrap 4 framework. This is a framework that uses a combination of CSS, HTML, and JavaScript, three of the most fundamental web development languages, to streamline front-end web development. Also, since DynamoDB is a NoSQL database, we will need to understand how NoSQL databases are organized in order to display our data on our web page. This will be a prominent topic of research for computer engineers going into the second half of this project. Next slide, please. In addition to working on the hardware and software connection next semester, our team hopes to incorporate modularity into our software. Given the speed at which new technologies emerge, smarter sensors and faster gateways are always on the edge. Our IoT system must be flexible enough so that updates to individual parts in our system will not interfere with the system as a whole. This is the concept of modularity. On top of learning modular programming techniques, our computer engineering team hopes to implement them into our system. Next slide, please. As a whole, our engineering team has high confidence to meet our anticipated best outcome. Our team plans to research any unfamiliar topics to proficiency, design the sections of our project that utilize these topics, and finally implement them into our final product. Our web server framework is what we need to work on to get our data to display on our site. Our hardware schematics will be updated to feature sensor placement on the machine. Our electrical engineering team is working on programming the PLCs for the project, as well as the E1 Flexi's implementation to interface with Amazon Web Services on the hardware side. We plan to finish our project strong with debugging and testing to not just make sure that the system works, but to ensure its longevity. Next slide, please. Before we conclude, we would like to acknowledge three individuals who helped us throughout the project. Dr. Harris Sunak pushed us to not just settle for achieving the standard, but to take pride in our work, whether it was in the Capstone lab or on our own. Electrical engineer Harm Groth helped explain many of the technical elements of the project in further detail and was available for any questions that we had. Consulting technical director Jeremy Peacock provided us with moral support and answered our questions about the Capstone program itself. On behalf of our Capstone team, thank you all for your support.